Assalamualaikum, Doctor. My name is Muhammad Hazwan Adalim bin Jumaris, and today I will present about gate pattern recognition of EMG signal processing with artificial intelligence approaches. So my supervisor is Dr. Izrin Farina Batishai. So this is my presentation outline. So we go into the first part. So in the first part is the introduction regarding to gate and FOG or freezing of gate. So definition of gate refer to human locomotion during walking or running. So the mechanism, it is complex, involves central nervous system, skeletal muscle and lower limb bones. And the third part is gate cycle, contain two phases, which are stance phase, foot contacts the ground, and the second phase is swing phase, foot move through the air. And the clinical importance regarding to the gait is the indicator of mobility and motor function, support diagnosis of neurological disorder, and monitor rehabilitation progress. So the second part is freezing of gait, FOG. It is a temporary inability to initiate or continue effective walking. So some people or patients often describe the experience as the distressing feeling that their feet glued to the floor. So it typically appears in the three ways, such as start hesitation, second part turning hesitation, and shuffling or trembling in place. So the common trigger by FOG is turning, narrow spaces or doorways, and environmental distraction or stress. So understanding normal gait and FOG is essential for developing a reliable EMG based system for automatic FOG detection. We go into the research scope and question. Research scope regarding to my project is first one, standardize the EMG signal processing pipeline. The second part is compare time domain TD, frequency domain FD, and time frequency domain features using ML machine learning and DL deep learning classifier under the same pre-processing pipeline. And the third one is to develop a hybrid multimodal ML and DL framework using EMG and Shank acceleration signal. So the research question come out from this research scope or this project is, how can a standardized EMG signal pre-processing pipeline improve the consistency and reliability of feature extraction for FOG detection? And the second question is about which combination of EMG feature representation, which are TD, FD or TFD, and AI classifier ML or DL provide the best FOG detection performance. And the last question is, can the proposed hybrid multimodal framework improve FOG detection compared with standalone ML or DL model? So let's go deep into the explanation about the three problem statement. So the first one is the lack of standardized EMG processing. So the current problem is EMG signal are highly variable and non-stationary, so it is making FOG detection challenging. And the existing studies use different pre-processing, segmentation, and also feature extraction method. And the research gap from this problem statement is no standardized EMG signal processing pipeline for consistent FOG detection. So the second part is, the second of problem statement is limited fair comparison of machine learning and deep learning. So the current problem is machine learning and deep learning approach have both been applied for FOG detection. However, most studies evaluate these approaches under different data sets, pre-processing techniques, and experimental setting. So the research gap is a comprehensive comparison of machine learning and deep learning model using a common dataset, and standardized processing pipeline remains limited. And the last one, the problem statement is lack of a robust hybrid framework for FOG detection. So the current problem is that integrating EMG and acceleration signal have shown promise for improving FOG detection performance. Nevertheless, few studies have combined the best performing ML and DL model into a hybrid framework and evaluated their performance using cross-subject validation. So the research gap is the development of robust hybrid models with strong cross-subject generalization remains. The first one is to develop a standardized signal processing pipeline for EMG-based gate data pre-processing, representation and feature extraction. The second is to evaluate the performance of machine learning and deep learning architecture for EMG-based gate recognition. And the last one, to design a hybrid multimodal AI framework, integrate optimal machine learning and deep learning for EMG and IMU, or acceleration-based gate recognition. So these are the literature review: signal acquisition, signal pre-processing, feature extraction and pattern recognition. So let's go one by one. So the kinetic, these signals relate to the force that act on the body to produce movement. So it is often used as the gold standard for identify gate events like heel strike. So the second one is, so the kinematic signal describe the motion of the body without regard to the force causing it. So it is typically acquired using IMU, physiological and neural signal, which is capture biological processes, which mean EMG. So it is measure the total activity of motor units. We use EMG to detect muscle activity before visible body movement occurs. So going to the next part, which is signal pre-processing. Filtering is about remove noise and keep useful muscle signal. So the second part is segmentation. So segmentation is about split the signal into smaller label sections. So instead of analyze one long recording, we break it into smaller pieces so the computer can learn from them. So the last part is a normalization. So normalization is we put all features on the same scale for fair comparison. So the Z-score is the zero mean and unit variance. Third part is a feature extraction. Many type of extracted features from the features category. So there are MAV, mean absolute value, STD standard RMS, and WL. Just to mention that from the time domain, it is used for the simple, efficient, and reflect muscle activity, while FD provide frequency information and identify muscle fatigue, while TFD it captures time vary patterns for CNN based learning. So the last part is the pattern recognition. So these are all the architecture used from the machine learning and deep learning from the past research paper. To summarize all this pattern recognition, for the ML was selected to represent well-established machine learning approaches, while CNN and LSTM from the deep learning chosen for the ability to learn spatial and temporal features. So these are the methodology for the project. Let's go deep through into signal acquisition. There are three channels: TAL, TAR, and DSR. So these are the channel or muscle of EMG we use for this project. And also signal obtained from the four tasks. Task 1, it is a multi-turn working. Task 2 is repeated task 1. And task 3 is the sharp turning, while task 4 is the repeated task 3. So the next part is signal pre-processing that contain filtering, segmentation, and normalization. So for the signal filtering, we use the notch filter 50 Hz. Then the bandpass of 10 to 499 Hz. It keeps only the frequency range that contain useful EMG, while remove the movement artifact and electronic noise. So after filtering, the EMG signal is divided into 3-second window with 90% overlap. So using high overlap, create more training sample and capture gate changes more continuously. So each window is then labeled as either FOG or non-FOG. So normalization we use is a Z-score, zero mean unit variance. So it used to standardize the extracted features to zero mean and unit variance. So this place all features on the same scale, prevent features with larger numerical values. So as a result, the model values evaluate every feature more fairly and achieve more reliable performance. So these are the normalization effect for the time domain and the frequency domain. And the last part is signal classification. Signal processing. So signal processing, so these are the representation from the signal processing of time domain, frequency domain, and time frequency domain. So the graph show that time domain representation. So the x-axis represent the time cycle, while the y-axis represent the amplitude. So it show how muscle activity changes over time, while it use time domain used to extract features such as Mpsw that we mentioned before, WL, SSC, and ZC or zero crossing. So the middle figure is about frequency domain. So the frequency domain convert EMG signal from the time domain to the frequency domain using the FFT. So instead of showing the signal occurs, it shows how the signal energy is distributed across different frequencies. So it used to extract mean frequency MNF and median frequency MDF. While the third one, the last figure, is about TFD, non-FOG and FOG. So TFD, of course, it combines both time and frequency using the STFT. So the color represent the signal intensity at different frequency over time. So we could summarize that each representation of TD, FD, and TFD capture different characteristics of the EMG signal. So all three are evaluated in this study to identify the most effective approach for FOG detection. So the last part is the signal classification. So this is our result got from the time domain, F domain, and TFD. So the TD time domain is the graph show the comparison of accuracy from the different classifier and combine or include all tasks. So as we can see that here, we can conclude that random forest RF has contribute more or high accuracy rather than the others. And it show that the task 4 is usually, or we can conclude that the channel combined from TA left, TA right, or GSR, when we combine all the channel together, we can obtain the high accuracy of this classifier from time domain. While the frequency domain, it shows that also the same thing as time domain, the accuracy for all classifier and all tasks. So in this section, we could see that task 3 obtain the high accuracy from the other tasks. While the last one is the TFD, time frequency domain. We can see that we use CNN and LSTM. So from both CNN and LSTM, it shows that CNN have high accuracy on task 3 in TAR muscle, while the LSTM shows that CNN contain high accuracy on task 4 on combined channel or combined muscle, TAL, TAR, GSR. So combine all together the muscle from the task 4 get high accuracy. While LSTM, it shows that task 3 show high accuracy from the muscle of TAR. So these are the confusion matrix that we obtain from the CNN. So if we calculate the non-FOG of 120 plus with 67 and divided by total of this box, we could get the value of accuracy. So I assume that it is about 90% above for the accuracy of this CNN of this task 4 with all channel. While the task 3 is confusion metric for the LSTM. So it shows that the task 3 has a high accuracy in channel 2 from the other tasks or the other channel. So these are the milestones of our project or of my project. Yes, we can see that my current project or my current method is currently on this type of WPT, package AI model development and comparative evaluation. So right now I am here at comparative number 4, comparative evaluation, all model, same condition and same metrics. So they are the two part of ongoing process for design and also the thesis submission. So these are the conclusion for my project on this day. The first one, to develop a standard signal processing, which is first objective. So we successfully generate figure illustrating the filtering, segmentation and normalization process to compare the process signal with the raw imaging signal. While the second part, to evaluate the performance of machine learning and deep learning, we also have analyzed the classification performance for both ML and AI-based approach. The target performance we got is 90% above accuracy for both AI approaches. Why ongoing process is to design a hybrid multimodal AI framework, integrate optimal ML and DL architecture for AMG and IMU or acceleration, specifically base case recognition. So we need to evaluate the hybrid classifier using accuracy, sensitivity and area under curve, AUC. So the target performance is about above 90% for all evaluation metrics. So these are my reference. So that's all about my project. So thank you.